What would a neutron star do to light? It would break one of your deepest visual assumptions almost immediately. Stand far enough away and you would still see a small, dead star hanging in darkness. But get closer and the rules begin to change. Its gravity is so intense that light no longer travels in anything like a straight line. Parts of the star that should be hidden around the far side begin to curve into view. From one position, you can see more than half of its surface at once. The object does not need to move to look impossible. Space itself is already bending the image. That distortion begins with scale. A neutron star contains more mass than the Sun, crushed into a sphere only about the size of a city. The result is an object so compact that its surface gravity becomes extreme. Let light pass near it, and the path folds inward. Distance compresses, edges misbehave. The star does not just shine into space, it reshapes the space the light must cross before it reaches you. That means the star never really looks simple. Its outline can appear warped. Hot regions near the surface can stay visible longer than they should as the star rotates. Even a pulse of light can be altered by the terrain of gravity around it. What seems like a clean beam leaving the surface is really a signal escaping from a deep gravitational well, dragged, bent, and stretched on the way out. And the surface it escapes from is nothing like a normal star. A neutron star is the collapsed core left behind after a massive star dies in a supernova. It no longer burns like the Sun. What remains is a compact remnant with a thin outer crust and matter packed so tightly that ordinary atomic structure cannot survive. Gravity crushes the surface into something brutally unforgiving. A fall of only a few meters would release enormous energy. Even a mountain there could be tiny by Earth's standards because the star's gravity refuses to let tall structures rise very far. The light leaving that surface can also carry the signature of heat far beyond what human eyes could comfortably imagine. Young neutron stars can glow in X-rays, turning them into objects understood better by detectors than ordinary vision. In visible light, the star may seem small and distant. In X-ray observations, it becomes violent and active, revealing hotspots, surface temperature differences, and the aftermath of collapse still written into its emissions. The eye would see a point. The instruments would see a physically intense remnant still radiating stored energy into space. Around some neutron stars, the magnetic field becomes extreme enough to shape the entire region nearby. Charged particles are funneled along the field and driven into the surface, helping create brilliant hotspots and powerful games of radiation. In the most extreme cases, the field can even change how light is polarized as it passes through the vacuum around the star. The space near the surface is no longer just empty distance. It becomes part of what the light has to cross, and part of what changes the signal before it reaches you. So the closer you get to a neutron star, the less reliable simple seeing becomes. You are no longer just looking at an object. You are looking through warped space, into high-energy radiation, across extreme magnetic structure, and down toward matter compressed beyond everyday intuition. The star changes not only what light does, but what seeing means. And that is the real payoff. A neutron star is not just a dead star with strong gravity. It is a place where vision itself becomes unstable, where the far side can bend into view, where a tiny sphere can outweigh the sun, and where a single point of light can carry the violence of collapse, pressure, heat, and warped space-time. Near a neutron star, light still travels, but it no longer behaves in a world your instincts were built to understand.